Hey yo, what is going on? It's your boy. So today we're going to be covering, going into complex numbers, a bit about how they are expressed, how they are drawn, how they are, multiplied, divided by, how they're added and subtracted by, and essentially how they're used. So, to begin with, we're going to talk a bit about the standard form. So the standard form is kind of the baseline way to express complex numbers. So it looks a bit like this. The a here is your real part. It's the real part of your complex number, and we say it's kind of the REZ if you wanted to express it in math terms. This part b is the imaginary term. It's the imaginary term. And we say it's like that. And so given that we have this standard form, we can also draw or kind of sketch what this would look like, what this complex number would look like on a Cartesian plane. So say I had this. My real axis is right here. Oops. My real axis is right here, and my imaginary axis is up here. So if my real number, let's take an example. My example was 5 plus 3i. Well, my imaginary number, first of all, is 3, so it would look like that. It would be 3. And then my real number is 5. And so the point would be right there. So that's your point. Now, one thing you can notice is that it forms a triangle. And the distance that the point is from the origin is something called our modulus. So that's called our modulus. The modulus is the distance of our imaginary or complex point from the origin. And recall that the modulus is just the hypotenuse. So essentially our modulus is the absolute value of z, which is equal to the square root of a squared plus b squared, given that the form our complex number is in is a plus bi. Now there's another term you should know, and it's called the argument. The argument is essentially the angle of your complex points with reference to the positive horizontal. The positive horizontal is right here. Oh, so that's kind of thick. The positive horizontal is right here. That's your positive horizontal. So we say that, so let's call this mod z. Our argument z is equal to theta, we'll call this theta, is equal to theta, where theta is equal to tan, the inverse or arctan of b over a. And so there's a couple considerations you should have when you're calculating the argument, because your imaginary complex point can fall in 4 quadrants. So I'm going to give you all the instances. So when your imaginary number and real number, when they're both greater than 0, they would fall in quadrant 1. And at this area, the way you calculate theta is simply tan negative 1 of b over a. So that's your first instance. Your second instance is when your imaginary number is positive, but your real number is negative. And so this would mean your point falls in quadrant 2. And in quadrant 2, your argument is equal to the inverse tan -1 of b over a, except now you add 180 degrees. So when both your real number and your imaginary number are negative, or in other words less than 0, your point falls in quadrant 3. And in quadrant 3, your theta is equal, your argument is equal to tan of -1 of b over a minus 180 degrees. Given that you're always looking at the angle formed with reference to the positive horizontal. And then your final instance would be in quadrant 4, where your real number is positive, but your imaginary number is negative. So in quadrant 4, the formula for theta is just tan -1 of b over a. So those are your 4 instances. So I think it might be useful we do an example. So let's say our example here was find the modulus and argument for, let's do one example with 2 plus 3i. So with 2 plus 3i, we're going to first find our modulus. So we said our modulus is equal to the absolute value of z, which is the square root of a, which in this case is 2, and the square root of 3. So that gives us square root of 13. So that's our modulus. Our argument, first of all, what formula are we going to use? We're going to use the quadrant 1 formula because 2 and 3 are both positive, so this point falls in the first quadrants. So we're going to do tan of -1, or inverse tan, of root 3 over 1 of root, not root 3 over 1, of 3 over 2. And that gives us a value of, in degrees, 56.3. And so that is the answer for that question. Another example could be b here. We can say -1 plus the root 2 of I. So same idea, we're going to do modulus of z, right? We want to find our modulus. And that's the square root of, in this case, -1 squared plus root 2 squared. And that's going to be simply 1 plus 2, which is root 3. Our argument, so let's consider which quadrant this is in. Well, our real number is negative, but our imaginary number is positive. So this will fall in the second quadrant. And to do this, it will be the tan of -1, or again, we can just say arctan, plus 180 degrees. So if I calculated this, so using a calculator, making sure your calculator is in radians, is in degrees, enter that into your calculator. So that gives me -54.7 plus 180. And so your final answer to 3 sig figs is 125 degrees. So that's a bit on standard form and drawing on the Cartesian plane. I think after this, something that might also be useful to know is actually doing actually conducting operations on these complex numbers. So let's move into that. So the next area is operations. And there are 4 types of operations, of course, you're going to have to know. So the first one is addition. And addition is pretty simple. When you have addition, so of 2 complex numbers given by z1 and z2, let's first define what z1 is. Z1 is a plus bi, and we can call z2 the same thing but with different variables. So maybe m plus ni. Here, this one's pretty simple. z1 plus z2 is just the sum of the real numbers plus the sum of the imaginary portions. So that's what your addition will look like. Your subtraction is kind of similar. So it will be z1 minus z2. That will be equal to the same thing except with minus signs. So a minus m plus b minus ni. With multiplication, what you're going to want to do is you're going to essentially just multiply them out. There's no real trick to this one. You're just kind of going to go with the flow. And then finally you have your division. This one is a bit different. So you'll have z1 over z2, which is equal to a plus, in this case, a plus bi over m plus ni. But notice, your denominator has a complex number, and that's not very favorable. So what we do to fix this problem is we multiply the fraction by its conjugate, by the denominator's conjugate. And what that means is we do this. The conjugate of any number is the binomial with the opposite sign. So if this is m plus ni, it would be multiplied by m minus ni. And the reason we can multiply this fraction by the conjugate is because if the top and bottom are the same, we're essentially just multiplying this value by 1. And when we multiply anything by 1, it still maintains its value. So, say I think this one requires a bit of an example. Say I had 1 minus 2i and 1 plus 3i. And I wanted to express this as, just a complex number in its standard form. How would I do that? Well, we first go about multiplying by the conjugate, which is in this case is 1 minus 3i over 1 minus 3i. And then that is equal to the bottom. Remember, the product of a minus the product of a. If I wrote this, if we called this a and we called this b, and b is just the conjugate of a, then our answer is simply a squared minus b squared. So our answer is just 1 squared, which is 1, minus 3i squared, which is 9i squared. Then on the top, this would equate to 1 minus 5i plus 6i squared. So now you notice we have this funky looking I squared term. So let me break that down for you. We know that I is equivalent to the square root of 1. I squared, therefore, is equivalent to the square root of negative 1 squared, which is just negative 1. I cubed is just I squared times I, which is negative 1i. I fourth is just 2i2s, I squares, which is just negative 1 times negative 1, which is just 1. So those are the 4 I values you'll need to know. But going back to the question, we can now simplify it. So 1 minus 5i plus 6 times negative 1 is negative 6 over 1 minus 9i squared. Remember, I squared is just negative 1. So 1 minus, or it becomes 1 plus 10, which is just 10. And if you simplified it, this becomes negative 5i minus 5 over 10, which is now just negative 1/2 I minus 1/2. But we like to express it in terms of real number first, and then the imaginary number. So it becomes negative 1/2 minus 1/2 I. And that's your answer. So I hope that made a bit more sense. Another concept that might be useful to know, especially now that I've introduced this idea of standard form, is maybe introducing polar form. And so what polar form is, let me just clear this. Polar form is another way of expressing a complex number. And as such, polar form is expressed as z, your complex number, r cos theta plus I sine theta. So your argument is the thetas. These are your arguments. And r is your modulus. And then z is the complex number you're expressing. Sometimes you'll also see the shorthand notation of polar form written as r cis theta. It's pretty much the same thing. So in order to convert from standard form to polar form, you're going to need to calculate your modulus and your argument, which we've already done in a previous example. So let's actually do one ourselves. So say z is equal to 3 minus 2i. And we wanted to convert this from standard to polar. So the first step we do is, well, we calculate r. We said r is simply the square root of a squared plus b squared. In this case, a is 3 and b is negative 2. So this gives us square root 13. Our arguments, we said our argument is simply tan negative 1 of 2 over 3, right? So remember, you always want to make reference to the quadrant. Remember what we talked about earlier? There are quadrants, and the quadrants will determine how you calculate your arguments. In this case, our point lays in quadrant 4, which means we can just use this formula. But there are also a couple of other formulas we went over, so keep those ones in mind. So this right here, now we're working in radians. So typically we work in radians when we work in polar form. So switch your calculator to radians, and if you calculate this, you'd see that you get negative 0.588. So if you express this as a polar complex number, you'd get square root 13 of cos negative 0.588, then plus I sine negative 0.588. And in shorthand notation, that would be square root 16 cis, and then your arguments, which in this case is 0.588. So that's how you do a polar form conversion. There's also another form you should familiarize yourself with, and that's called Euler's form, or Euler's form, however you like to say his name. And this is expressed as the z, re, which is E is Euler's number, or Euler's number, to the power of I, and then your arguments. So this is your argument, this is your modulus, and this is your complex number. And so as you're doing this, just keep in mind that always you're going to always want to start off with first finding your modulus and your arguments. So if we take an example, the one we did before, z equals 3 minus 2i, we just take our r value, which in this case is 13, or sorry, square root 13, and our argument, which is negative 0.588, and we just plug it in. So this would be z is equal to square root 13 ei, and then our theta is negative 0.588. And that's how Euler's form would look like. So hopefully that kind of makes a bit more sense. So moving a bit forward with the operations we were talking about earlier, one operation I didn't go over was powers and raising complex numbers to powers. Now, to do that, you're going to have to use de Moivre's theorem. So, de Moivre's theorem. And so, this helps us evaluate the powers of complex numbers. De Moivre's theorem is denoted as z to the n, which is equal to r cos theta plus I sine theta to the n, where theta is equal to your arguments, and r is equal to your modulus, and n belongs to the set of natural numbers. So to do this, the formula, if we have a complex number in that format, we'd evaluate this doing the following. So this would equal r to the n cos n theta plus I sine n theta. So let's do a bit of an example, because the scene's a bit daunting. So say I had 2 cos 40 degrees plus I sine 40 degrees to the 6th. Now, according to de Moivre's theorem, all we have to do is take our r and raise it to the 6th. So 2 to the 6th. And then what we do is, after that, we take our argument and multiply it by n. So 40 degrees times 6 plus I sine 40 degrees times 6. And then we just simplify from there. 2 to the 6 is 24. Cos, this becomes 240 degrees. And then we add I sine of 240 degrees. After that, we just simplify. So recall your trigonometric circle. Cos 240 is the same as saying cos 60 in quadrant 3, right? So if we do that, cos 60 in quadrant 3 is just negative 1/2. And then after that, we can do the same for sine. Sine 240 is like saying sine 60 degrees in the 3rd quadrant. So that would just become negative root 3 over 2. And then you evaluate it. So then this becomes negative 32 plus I sine Or, sorry, you don't need this. When you evaluate the values, you keep it at that. My bad. So then so if you multiply that out, your answer would be negative 32 minus 32 root 3i. That's your answer. So if I had a question like this, and it's asking me to evaluate it, right now it's this number right here, it's in standard form, but the Moivre's theorem can only be executed in the polar form. So we're going to have to convert this to polar first. Remember, the way we do this is we first calculate r, and in this case r is just 1 squared plus 1 squared. The 1 is right there, and this will give us root 2. We also calculate our argument theta, or our argument, as first we determine, well, what quadrant is this in, and we know that both our real number and our imaginary number are positive, so it's in quadrant 1. So our formula would be tan negative 1 of 1 over 1, and this is just equal to root 2 over 2. So, sorry, not root 2 over 2, pi over 4 in radians. So given that, we now express this as a polar complex number. So z is equal to root 2 of cosine pi over 4 plus I sine pi over 4. And we raise this entire expression to the 5th power because we've equated it to our standard form variation. So if we do this, now we can use the Moivre's theorem. So z is equal to 2 raised to the half power to the 5. And then we multiply that by cosine pi over 4 to the times 5 plus I sine pi over 4 times 5. So z is equal to, well, we have 2 to the power 5 over 2, but we can break that up into two powers. So this will become 2 raised to the 2 plus, or sorry, times 2 to the 1/2. And if we do that, this becomes, this becomes 4, and then this becomes root 2. So that's our simplified r. And then we have cos, of course, 5 pi over 4 plus I sine of 5 pi over 4. Now, we can go further, and we can actually evaluate what those two values are. So cos 5 pi over 4 is like saying cosine pi over 4, but in the third quadrant. So it would become negative root 2 over 2, and then the same for sine. So sine 5 pi over 4 is like saying sine pi over 4 in the third quadrant, which is also negative root 2 over 2. And now we just do our magic. So then this becomes negative 4 minus 4i, if you expanded it out. So that's our answer. So moving on to our last thing, which I think is relatively important, is finding roots of a complex number. I'm not too sure if this is in the IB curriculum, but I think it's worth knowing because why not? So let's try and find the roots of a complex number. And so to do this, we have a bit of a formula. So z to the k is equal to the nth root of r, cosine theta plus 360 degrees, or 2 pi k over n, plus I sine of theta, your argument, plus 360 degrees again, or 2 pi k over n. And I know this seems a bit daunting, but I'll break it down for you. Essentially, n is your number of roots. K is equal to 0, is the entire range from 0 up to 1 minus n, or n minus 1. And then these are the parts you'll want to evaluate first. So I will show you an example. Say I wanted to find the roots of, or all 5 roots. So find all 5 roots of 32 cosine 150 degrees plus I sine 150 degrees. So say I wanted to do this in, let's say, polar and standard form. So if I wanted to do this, I'll first have to calculate what n is. And because I want to calculate 5 roots, n is equal to 5. And k is equal to 0, 1, 2, 3, 4, all the way to n equals 1, which is, in this case, 4. So these are the 2 values I know right off the bat. After this, I will want to calculate essentially what I underlined here in blue, for all values of k. So when k equals 0, I will have theta, or I will have, in this case, our theta is 150. So 150 degrees plus 360 degrees, and then I substitute k for 0 over n, which in this case is 5. And that equals 30 degrees. Then I do the same for k equals 1. For k equals 1, it becomes 150 degrees plus 360 degrees over 1 over 5. Times 1 over 5. That gives you 102 degrees. Note that they do jump by this jump here is 72 degrees. For k equals 2, it becomes 150 degrees plus 360 degrees times 2 over 5, and then this is just a 72 degree increase from the last, which in this case is 174. So even without the formula, now I can calculate it. 72 plus 174 is 246 degrees. K equals 4 will just be 72 degrees more than that, which is 318. After I calculated all this, I can now plug in my values. So for k equals 0, it becomes 2 cos 30 degrees plus I sine 30 degrees. For k equals 1, it becomes 2 cos 102 degrees plus I sine 102 degrees. For k equals 2, it becomes 2 cos 174 degrees plus I sine 174 degrees. For k equals 3, it becomes 2 cos 246 degrees plus I sine 246 degrees. For k equals 4, it becomes 2 cos 318 degrees plus I sine 318 degrees. So these are your roots. These are your roots in polar form. To find in Cartesian form, you just evaluate and expand. So if you evaluated and expanded these values and you plugged it into a calculator, you'd have root 3 plus, I believe, I. Then you'd have negative 0.416 plus 1.96i. Here you would have negative 1.99 plus 0.209i, and so on and so forth. One thing you will note is that these roots all have the same they all have the same absolute value. In other words, their modulus is equal to each other. So in this case, our modulus for each number is 2. And that will hold true for every root of this complex number. So if you're given 5 complex numbers, you can actually determine if they are all roots of each other, if they have the same modulus. So I hope that helped a bit. If you have any questions, again, feel free to comment in the comment section down below. And hopefully that made a bit of sense.